Section 5.3, Complex Vector Spaces. If n is a positive integer, then a complex n-tuple is a sequence of n complex numbers, v1 through vn. The set of all complex n-tuples is called complex n-space and is denoted by Cn. Scalars are complex numbers, and the operations of addition, subtraction, and scalar multiplication are performed component-wise. So for example, let v be this complex vector right over here, and we'll let A be this complex matrix. Let's find V bar, real part of V, imaginary part of V, A bar, real part of A, imaginary part of A, and determinant of A. So for starters, V bar, which we'll say is the conjugate of V, is, instead of 3 plus I, 3 minus I, and instead of negative 2i, it'll be positive 2i, and then 5 just stays 5. The real part of V is just the part without the imaginary part, so that's 3 from the 3 plus vi, and then it's 0 from the minus 2i component, and then 5, the entire last component, is real. The imaginary part is just 1 because it's 1i for the first component, and then minus 2 because that's the coefficient for I in the second component, and there is no I in the third one, so just 0. Then if we want A bar, that's equal to 1 minus I, 4 I, and 6 plus 2i. Because all we do is just change this to a minus, this to a plus, this to a plus. Then if we want the real part of A, that would just be 1, 0, 4, 6. And if we want the imaginary part of A, then that's just 1 minus 1, 0, minus 2. Okay, last but not least, how about we get the determinant? So the determinant of A will just be the determinant of 1 plus I, 4 minus I, 6 minus 2i, and then multiplying we get that's 1 plus I times 6 minus 2i minus I times 4. And if we do the multiplication, work things out, remember I squared is minus 1, we end up with 8 plus 8i. If u and v are vectors in Cn, and if k is a scalar, then bar u, in other words, the conjugate of the conjugate, is just u. Cancels. The conjugate of ku is the same thing as the conjugate of k times the conjugate of u. Conjugate of u plus v is just the conjugate of u plus the conjugate of v, and the conjugate of u minus v is just the conjugate of u minus the conjugate of v. If A is an m by k complex matrix and B is a k by n complex matrix, then bar A is A, bar of A transpose is the transpose of A bar, and bar of A times B is just bar A times bar B. If u equals u1 through un and v equals v1 through vn are vectors in Cn, then the complex Euclidean inner product of u and v, also called the complex dot product, is denoted by u dot v, and it is defined as u1 v1 bar plus u2 v2 bar, and so on. So this is very similar to the dot product we know of, where we just take each component and multiply it and add them. The only difference is you have to be very careful. The second vector that you're looking at, you have to take the conjugate of every single one of the components when you multiply them. We also defined the Euclidean norm on Cn to be norm v equals the square root of the dot product of v dot v, which is the square root of the length of v1 squared plus the absolute value of v1 squared plus the absolute value of v2 squared, and so on. How about we find u dot v, v dot u, absolute, the length of u and length of v for the vectors u and v given over here. Okay, so we'll first get u dot v, and that's 1 plus I times 1 plus I bar plus I times 2 bar plus 3 minus I times 4I bar. So that's 1 plus I, and then 1 plus I bar is just 1 minus I, plus 2I, because 2 bar is just 2, plus 3 minus I times minus 4I. And altogether, when we simplify, we get that that's minus 2 minus 10I. Let's get v dot u now. So v dot u is 1 plus I times 1 plus I bar plus 2 times I bar plus 4I times 3 minus I bar, and that equals 1 plus I times 1 minus I minus 2I plus 4I times 3 plus I, which is minus 2 plus 10I. So notice there are conjugates, u dot v and v dot u. Before, u dot v was always equal to v dot u, but now we can see that it's not commutative in the case of the complex vectors. Let's look at the length of u. So the magnitude of u, that'll be, well, we'll take all these absolute values and square root them after. So absolute value of 1 plus I squared plus absolute value I squared plus absolute value of 3 minus I squared, and we'll take the square root of all of that. So that's the square root of 2 plus 1 plus 10. And that's just the square root of 13. How about the length of v? Okay, so we'll have 1 plus I squared again, plus 2 squared this time, plus 4I squared. And that ends up being the square root of 2 plus 4 plus 16. So that's the square root of 22. If u, v, and w are vectors in Cn, and if k is a scalar, then the complex Euclidean inner product has the following properties. U dot v is the conjugate of v dot u, which makes sense considering that we basically saw that in the previous example. U dot v plus w is u dot v plus u dot w. That product is still distributive over addition. The scalar distributive property still holds. K times u dot v is ku dot v. U dot kv is k bar u dot v. You have to be careful when you're distributing to v, because it distributes to u without the conjugate, but if you're distributing it to v, then you have to conjugate the k. v dot v is greater than or equal to 0, and v dot v is equal to 0 if and only if v is 0, same as before. If lambda is an eigenvalue of a real n by n matrix A, and if x is a corresponding eigenvector, then the conjugate of lambda is also an eigenvalue of A. X bar is a corresponding eigenvector. Let's prove this real quick. Since lambda is an eigenvalue of A, we're assuming lambda is an eigenvalue of A, we want to now show that we have that the conjugate is also an eigenvalue. Well, since lambda is an eigenvalue of A and x is a corresponding eigenvector, we have that AX is lambda x, so that means that the conjugate of AX is the conjugate of lambda x, which is the same as conjugating lambda and conjugating x separately. But remember that we have a real n by n matrix A, so that means that the conjugate of A is equal to A. So that means that we have that the conjugate of AX, which is the conjugate of A times conjugate of x, is just A times conjugate of x. The conjugate disappears for A. So that means that we have A times conjugate of x equal to the conjugate of AX equal to the conjugate of lambda times the conjugate of x. But we know that the conjugate of x is not equal to 0 because x is not equal to 0. So that means that lambda, the conjugate of lambda must be an eigenvalue of A, because A times the conjugate of x is conjugate of lambda times conjugate of x. It's a definition of what an eigenvalue is, and that means that x bar is the corresponding eigenvector. Cool, so that means that anytime we find an eigenvalue for a complex matrix, we get a free eigenvalue in its conjugate. Let's look at this matrix over here and find the eigenvalues and basis for the eigenspaces of it. So first of all, let's find the eigenvalues. We'll look at the determinant of lambda I minus A. So that means that we're looking at lambda plus 2, because lambda minus minus 2 is lambda plus 2, and then minus minus 1 is plus 1, minus 5, and then lambda minus 2. And when we take this determinant, we get lambda squared plus 1. Lambda plus 2 times lambda minus 2 minus minus 5. So that means that we can factor that as lambda minus I and lambda plus I. Okay, so that means that we've got eigenvalues of I and minus I, which makes sense, they're conjugates of each other. So how about we solve the equation where we multiply by x, set it equal to 0 in order to find the eigenspaces. So in other words, we're looking at the matrix lambda plus 2, 1, minus 5, lambda minus 2 times the vector x, we'll write that as x1, x2, and set that equal to 0, 0. Okay, so solving for x, let's first try the case where lambda is equal to I. Oh, not 1, it's I, and that'll be for our first eigenvalues. So substituting in for lambda, we get I plus 2, 1, minus 5, I minus 2 for our matrix. And we will multiply that by x1, x2, and set it equal to 0, 0. So then I'll join the 0, 0 column to get I plus 2, 1, 0, minus 5, I minus 2, 0. And I'll reduce that. So I'll swap the two rows. So I'll take this top row and I'll move it over for this row. But then I'll just take this entire row and just multiply it by 0. so that I get all zeros. And then the bottom row, this row that becomes the top row, I'll just divide by -5. Oh, so this will be zeros in the bottom now because I'm swapping these two. And the -5 I'll divide and I'll get 1. And the I-2 I'll divide by -5 and I'll get 2/5 minus 1/5 I. Okay, so then that's reduced. I have my leading 1, good to go over there. So I can just set x1 equal to -2/5 plus 1/5 I times t, because my free variable x2, which I can just make equal t. So I'll just set x2 equal to t. Okay, cool. Because notice I have x1 plus this thing times x2 equals 0, so I just subtract off this and then set that equal to x1. So that means that my vector x is equal to, for the x1 component, -2/5 plus 1/5 I, and then 1 for x2. Because I have a t in here, remember, and I'll just factor out the t, and then it's just any multiple of this for my bases. There's only one vector in it, so I'll just take x and set x equal to this vector for my basis. I'm just choosing a particular value, but any scalar multiple of this would work. So I'll take a times x equal to -2 -1 5 2, and x, I'm going to take -2/5 plus 1/5 I, 1, and then multiplying out, I get -2 times -2/5 plus 1/5 I minus 1 for my first component, and then 5 times -2/5 plus 1/5 I plus 2 for my second component. Simplifying, we get that equals -1/5 minus 2/5 I, which is just I times x. Just basically testing that, yeah, this actually is an eigenvector that works with eigenvalue I. Okay, how about we take a look at the other case we had where lambda was equal to -I. Okay, so then x should just be the conjugate of the x that we got before. So we shouldn't have to go through all the work of solving for it again. So it should just be -2/5 minus 1/5 I and 1. Because all I have to do is just take that plus and turn it into minus. So let's test that. Let's take a times x bar. So that's -2, -1, 5, 2. And we'll multiply that by -2/5 minus 1/5 I, 1. And it becomes -2 times -2/5 minus 1/5 I minus 1, and 5 times minus 2/5 minus 1/5 I plus 2, which equals minus 1/5 plus 2/5 I minus I, which is minus ix. Wonderful. Or minus ix bar. So minus I is an eigenvalue with eigenvector x bar, as we would have liked to see. Excellent. If A is a 2x2 matrix with real entries, then the characteristic equation of A is lambda squared minus trace A lambda plus determinant of A equals 0, and A has two distinct real eigenvalues if trace A squared minus 4 determinant of A is greater than 0. A has one repeated real eigenvalue if trace A squared minus 4 determinant of A equals 0, and A has two complex conjugate eigenvalues if trace A squared minus 4 determinant of A is less than 0. This should kind of make sense, because if I were to write an arbitrary matrix A equal to, let's say, A, B, C, D, and I take the determinant of lambda I minus A, then that'll be lambda minus A minus B minus C lambda minus D, and that would be lambda minus A times lambda minus D minus BC, which is lambda squared minus A plus D lambda plus AD minus BC. So notice A plus D, that's the trace. AD minus BC, that's the determinant. And remember from algebra that if we have B squared minus 4AC positive, then we have two real roots. So we have two real eigenvalues in this case. Remember that A is the coefficient on x squared, B is the coefficient on x, and then C is your constant. That's the discriminant. So if the discriminant is equal to 0, you have one repeated real root, so one repeated real eigenvalue. And if the discriminant is negative, then you have two complex conjugate roots, so two complex conjugate eigenvalues. How about we now use the characteristic equation to find the eigenvalues of these three matrices. So for the first one, how about we calculate the trace and the determinant? So if we just add up 2 and 5, we get the trace just by adding up along the diagonal. So the trace of A is 7, and the determinant of A is 5 times 2 minus 2 times minus 1, so that's 12. So together, that gives us the characteristic equation. So now we have lambda squared minus the trace, which is 7, times lambda plus 12 is equal to 0. So that gives us eigenvalues, because we could just factor that as lambda minus 4 and lambda minus 3 equals 0. So we have lambda equals 4 and lambda equals 3. Notice we have two distinct eigenvalues because we have b squared minus 4ac positive. For the next one, how about we get the trace and the determinant again? So the trace is 2. The determinant is 1. So that tells us, oh, I forgot my arrow over there. So that tells us that we have lambda squared minus 2 lambda plus 1 for our characteristic equation, and that means that we have lambda minus 1 squared equals 0 when we factor, so we have a repeated eigenvalue of lambda equals 1. Makes sense, because b squared minus 4ac is 0. Now if we look at the trace of a for the last one, we get that that's 4, and the determinant of a is equal to 13. So we have lambda squared minus 4 lambda plus 13 equals 0. So that means that we have to use the quadratic formula to find the solutions to this, because it does not factor over real numbers. So we have 4 plus or minus the square root, b squared minus 4 is c, so that's minus 4 squared minus 4 times 13 all over 2a, which is just 2. So that gives us 4 plus or minus square root of minus 36 over 2. So that's 2 plus or minus 3i. So we have eigenvalues of lambda equals 2 plus 3i and lambda equals 2 minus 3i. If A is a real symmetric matrix, then A has real eigenvalues. Let's prove this. Suppose that lambda is an eigenvalue of A and x is a corresponding eigenvector, where we allow for the possibility that lambda is complex and x is in Cn. Therefore, we have ax equals lambda x, where x is not equal to 0. If we multiply both sides of this equation by the conjugate transpose of x, and use the fact that the conjugate transpose of x times ax is equal to conjugate transpose of x times lambda x, we just substitute lambda x for ax, and then we can pull out that lambda, right? So then we have conjugate transpose x times x, and we get, that's the same thing as lambda times x dotted with x, which is lambda times the magnitude of x squared. So that means that we'll just have to divide both sides by that. So we'll put that over here. Remember, x is not 0, so we can do that. So that means that lambda is equal to conjugate transpose of x times ax divided by length of x squared. Since the denominator in this expression is real, we can prove that lambda is real by showing that the conjugate of the numerator is equal to itself, basically. But A is symmetric, and it has real entries. So therefore, if we look at the conjugate of the conjugate transpose of x times ax, so then we move over the conjugate to the x and the conjugate to the ax, but the conjugate of the conjugate will cancel, so we just have transpose of x times the conjugate of ax. But that's the same thing as writing the conjugate of ax transpose times just x, right? We can change the order by changing the transpose. So then we move over the conjugate onto a and onto x. But we already know that a is real, so conjugate of a is just a. So then we can just distribute the transpose by changing the order. So the conjugate x gets the transpose and the a gets the transpose, but the transpose of a is just a, because our assumption is that a is real and symmetric, where a is equal to its transpose. So that's why that was very important, and therefore we just get that it's conjugate transpose of x times ax. So that means that the conjugate didn't change the numerator, which means the conjugate didn't change lambda, so that means that lambda is real. So A must have real eigenvalues. let's next prove that the eigenvalues of the real matrix C, where C is equal to A minus B, BA, are lambda equals A plus or minus BI. If A and B are not both 0, then this matrix can be factored as this thing right over here, where we have the absolute value of the eigenvalues on the diagonal, 0 otherwise, and we have the cosine of the angle from the positive x-axis to the ray that joins the origin to the point AB. To prove this, the characteristic equation of C is lambda minus a squared plus b squared equals 0, from which it follows that the eigenvalues of C are lambda equals a plus or minus bi. Assuming that a and b are not both 0, let's let phi be the angle from the positive x-axis to the ray that joins the origin to the point AB. Then the angle phi is an argument of the eigenvalue lambda equals a plus bi. So we have a equals absolute value of lambda cosine phi. Right? B is absolute value of lambda sine phi. So we can write the matrix C as this thing right over here. But then, like we said, A is equal to absolute value of lambda cosine. So we just replace that with A. We cancel the lambda because lambda is not 0. And we just end up with exactly what we wanted to prove. It turns out that this theorem is kind of useful because we can actually factor matrices into matrices that contain this form given certain conditions, as this next theorem shows. So let A be a real 2x2 matrix with complex eigenvalues lambda equals a plus bi, where b is not 0. If x is an eigenvector of A corresponding to lambda equals a minus bi, then the matrix P, which is equal to the real part of x and the imaginary part of x, is invertible. And we have A equals P times that matrix that we just got from the previous theorem times P inverse. So as an example, how about we factor the matrix in example 3 into the form given in this theorem, 5.3.8, using the eigenvalue lambda equals minus I and the corresponding eigenvector previously obtained. So we've got lambda equals minus I, and that gives us an x equals minus 2/5 minus 1/5 I, 1 for the eigenvector. And in this case we have A equals 0, B equals 1, the real part of x is equal to minus 2/5, 1, and the imaginary part of x is equal to minus 1/5, 0. So then we have P is equal to the real part of x and the imaginary part of x, and that's equal to minus 2/5 minus 1/5, 1, 0. So we end up with minus 2, minus 1, 5, 2 for our matrix from example 3, which we can rewrite as that matrix P minus 2/5, 1 for the real part, minus 1/5, 0 for the imaginary part, times 0, minus 1, 1, 0, times 0, 1, minus 5, minus 2 for the P inverse, which I sort of squeezed in there a little poorly, and I also didn't show you calculating P inverse, but it's not too hard because it's a 2 by 2 matrix.